We now have our feet wet with matrix multiplication, and it's important to really get a good concept of how this works. So we'll look at a couple more examples here. And the most important thing to note is that matrix multiplication is not the equivalent to matrix addition, in that we notice that to have matrix multiplication occur, it's not essential that both of our matrices have the same size. So the one thing that I just want to point out up front is that matrix multiplication is defined differently than matrix addition. And we have this very bizarre definition for the way matrix multiplication takes place. We'll see that for application purposes, that is actually a very nice definition. But on first look, when you see something like this, you have two matrices of the same size that you want to multiply together. This right here is unfortunately not equal to 1 times 2, 2 times 4, 3 times 6, 4 times 8. So notice this big not equal to. This is not how we multiply matrices. It does not work the same way as addition. There are instances where we want to do what is called pairwise or element-wise multiplication, and there are applications, software applications out there, such as Python, that will do this, but this is not how we multiply matrices. In fact, if this matrix right here, if we call this A and we call this B, the way matrix multiplication takes place is A times B for these two examples will be, you'll have a matrix that consists of the columns of B multiplied by matrix A. So I'll call this B1 and I'll call this B2. So what we'll do for the matrix product is we'll take the A matrix and we'll multiply, we'll do a matrix vector multiplication with A and B1. Now that's going to create a column, so I'm just going to kind of draw these lines and indicate that's going to be a brand new column in there. And then in the second column over here, we're going to have A times B2. And these are distinct columns. They're not going to be added or combined. We're going to form two brand new columns. And this in part helps explain the dimensionality of what it is that we're doing. We have two rows in this matrix over here, and we're multiplying by one column, which means we're going to take A, we're going to scale 1, 3 by the 2, we're going to scale 2, 4 by the 6, and we're going to add them together. So we're adding together scale multiples of two 2 by 1 vectors, which means that this is going to be a 2 by 1 vector. But we're going to have to do that for the second column as well. We're going to have to do that for this column here and multiply the same two components by each of the two vectors in matrix A. And since we're going to add the two 2 by 1 vectors, we're going to get a brand new 2 by 1 vector. So this matrix here is going to have two rows and it's going to have two columns, and therefore its result is 2 by 2. The number of columns that this has depends on the number of columns that we have in our B matrix, because each one is going to represent one of these two products. And then the number of rows it's going to have is the same as the number of rows as A has, because those are the vectors that are going to be linearly combined. Okay, let's take a look at an example of a situation where we have matrices that are different sizes. So I'm going to take a 2 by 3 matrix, 2 rows, 3 columns. I'll put 1, 2, 3, 4, 5, and 6 in here. And then I'll have a 3 by 2 matrix, which we'll have, we'll just say 2, 4, 6, 0, 1, 1. All right, so we have a 2 by 3 and a 3 by 2. That means each of the vectors in the second matrix is going to scale and linearly combine the columns of the first matrix. So what we're going to have in here is, well, another way I could write this is that we have 3 vectors here that are going to be linearly combined, hence why our dimension of our final matrix is going to be 2. Since the inner dimensions match, we're going to have 2 by 2. Now it's important that the inner dimensions match because each one of these values here has to have a column to scale. So there are 3 columns in the first matrix. There are 3 elements, there are 3 rows that are each going to scale one of those columns. So I'll have 2 times this vector plus 4 times this vector plus 6 times this vector. So that's going to give me 2 times the 1, 4 vector plus 4 times the 2, 5 vector plus 6 times the 3, 6 vector. And that's just going to be the first column. Now I'm going to have to do the same thing and form a brand new column in my matrix. So we could think about this right here as A times B1, where if this is matrix A and this is matrix B, then this is B1 and this is B2. And this is matrix B. So now I need to form A times B2. So what I want to do is I want to take these elements here and form the new column when 0 multiplies the first column of the first matrix, 1 multiplies the second column of the first matrix, 1 multiplies the third column of the first matrix. We're going to have 0 times the 1, 4 vector plus 1 times the 2, 5 vector plus 1 times the 3, 6 vector. So really all this is a linear combination of several linear combinations, in fact. In this case, specifically 2 of them, since we have 2 columns inside of the B matrix. And this is just a way to do all of this in one shot. So you'll notice that what we end up getting here is 2 times 1 is 2, plus 8 is 10, plus 18 is 28. I'll have 8 plus 20 is 28, plus 36 is 64. And there's my first 2x1 column that I get from linearly combining 3 2x1 vectors. And then in my second column, I'll have 0 plus 2 plus 3 is 5. And 0 plus 5 plus 6 is 11. And this is my final matrix, which you can see is a 2x2 matrix. If we had a third column inside of the B matrix, then this would end up being a 2x3, because then for that third column, we would again need to scale and add all of the vectors inside of matrix A. Now, another way of viewing this, of course, is that we're taking 2 times 1 plus 4 times 2 plus 6 times 3, and that's really just the first row, which gives us the 28. And then we could do the second row, 2 times 4, 4 times 5, 6 times 6, which is exactly what we did with these 3 lower elements. And we repeat the same thing for the second vector. Let's go ahead and take a look at another example where we have a 2x2 matrix multiplying a 2x3 matrix. So on quick glance, we can see that the number of columns in the first matrix is indeed the same as the number of rows in the second matrix, and therefore this product does exist, and our resulting matrix will be a 2x3. So let's see how that's going to take place. First of all, we're going to start with the first column. We're going to start with those first 2 elements. Instead of thinking about it as a column, I'm going to think about it as 2 elements, each of which are going to scale our 2 columns to produce A times B1. Now, for the first set of values, I'll have 1 times the column 1, 3, plus 5 times the column 2, 4. And that right there is my product between my matrix vector product between A and B1. So we'll call this result A times B1. Now we'll do the same thing for B2. We'll call this B2. And now we're going to take this element times the first column of A, and this element times the second column of A, and we're going to add those results together. So I'm going to leave myself enough space here. So it's going to be 2 times the column 1, 3, plus 0 times the column 2, 4. And what I've just formed here is the product between A and B2. Finally, we'll go ahead and do the same thing for B3 because now we have a third column that also has elements which need to scale matrix A. And so I'll just leave myself enough space here to say this will be 1 times the vector 1, 3 plus 1 times the vector 2, 4. And that's it. So I'm going to go ahead and close this matrix. And this is going to be A times B3. Now I'm ready to evaluate all of this. But one of the important things to keep in mind is that I'm going to write this one other way. So the top element is going to be 1 times 1 plus 5 times 2. The bottom element is going to be 1 times 3 plus 5 times 4. The reason I'm writing it like that is just to see that 1 and 5 are going to scale the top and bottom components of these two vectors and then add their result together. So 1 times 1 plus 5 times 2 is going to be the new top element in the first row, first column. So if we're taking the first row here by the first column here, that's going to give us our first row by first column. Now keep in mind this is just one number right here. It's just we haven't combined those values. Same thing here, that's a second number. And now we could also see that for the second column, we're going to have 2 times 1 plus 0 times 2, which is the same thing we get here in this vector product, 2 times 1 plus 0 times 2. This just gives us another way to multiply matrices or to think about multiplying matrices. 2 times 3 plus 0 times 4 is the same thing we would get if we took 2 times the bottom component plus 0 times the bottom component. So 2 times 3 plus 0 times 4. There's our, again, now we took the second row by the second column, so we're going to be in the second row, second column. And then here we would get 1 times 1 plus 1 times 2, which is exactly the same thing we get when we do the linear combination. And then finally, we have 1 times 3 plus 1 times 4. And we'll go ahead and close that matrix. And there is our 2 by 3 matrix that we're going to get. And we could condense these values down, but I'll go ahead and leave it like this. So there's really two ways of thinking about matrix multiplication. If we have a matrix A, which I will just describe as an m by n, so that means it's going to have A11 all the way up to A1n, and we'll have m rows, so AM1 all the way up to AMN. And then we have a matrix B, which is, okay, wait a minute, how big does this have to be? It doesn't have to be m by n. It's important that the inner dimensions match, so this would have to be an n by something. So I'll say n by p to indicate that this could be a totally different number than m is over here. And so this will be B11 all the way up to, it has p columns, so this will be first row, pth column, down to the nth row, Bn1, all the way over to the pth column of the nth row. Now, one way that we just thought about this in specifically right here is, well, certainly we could do call these columns B1 all the way up through BP. And so we can think about A times B as being the matrix consisting of the matrix vector products AB1 all the way up to A times BP. Or another way to think about this, we could say that A times B is really just all of these elements right here multiplied by all of these elements right here and added together. And that's exactly what we did right up here. So how would that look? Well, that would begin to look something like this. It can get quite messy, so we won't list out all of the products, but this first component will be A11 times B11 plus A12, which would be the second element here, times B12 plus A13 times B13 plus etc. until we get to A1n times Bn1. And similarly, we would do the same thing with the second row of elements. We would multiply that by B11 through Bn1. And this, remember, this is just one value right here. So in our second row, which we would have A21 through A2n, we would have B11 or A21 times B11 plus all the way down the line, all the way up to A2n times Bn1, and that would be our second, that's just a single number right there, and we would kind of repeat that process with each of these rows until we got to the bottom one, which would be Am1 times B11 plus etc. all the way down to Amn times Bn1. And that's just a single value once again, right there. Now we would need to do this for all of the columns. We would need to move on to this column and then this column and then this column, which would have the corresponding values inside of the matrix. So this is just another way to kind of think about matrix multiplication as a bunch of element-wise products all added together. And you can see that this is what we would normally kind of define as what we would call dot product. So it's a bunch of dot products. And these two forms, whether we think about it as we're going to let the columns of B be the scalars in the linear combination of the columns of A. Here we're doing exactly the same thing. We get the exact same answer, but it's a little messier, but sometimes it's more convenient in certain applications to think that way.